Hey, this is Leach with Simpson Math, and in this video, we will be taking a deeper dive into the conic section known as the ellipse. In a previous video, we defined it, but let me do a quick review. If you see, we have 2 points. They are each known as a focus, collectively plural foci. I have a distance drawn from each focus to a single point xy. And what's special about this is that the sum of these two distances, which we call d1 and d2, will always equal the same value for all points on the ellipse. In this video, we'll be looking a little bit more specifically at some of the other relationships across this ellipse. So let me get started by drawing a line segment across the from one end of the ellipse to the other that goes through my two foci. We call this the major axis. On your homework, I'll be asking you to define the equation of this major axis. Secondly, we have a minor axis. It is perpendicular and halfway, I guess you can say it's a perpendicular bisector of that major axis. So I'll go ahead and mark that perpendicular box for that perpendicular symbol. So it cuts the major axis in half. The intersection of those two axes is going to be the center of the ellipse, h comma k. In this case, it is 2 comma 1. All right, so there's my ellipse with my center marked at h comma k, my major axis, which is the longer one, and then the minor axis, which cuts it in half and is perpendicular. If you think back to the parabola from the previous video, that h comma k is used at the vertex of the parabola. Here, for the ellipse, our h comma k is defining the center of the ellipse. But we do have vertices. They are sort of the endpoints of those axes. So I have a major vertex 1 and 2. Whether I'm defining 1 and 2 just so that way they're notable that they're two different points, but they're just our major vertices. And then we have our minor vertices on the end of our minor axis. Those 4 points will define our ellipse for us. So that's all that I need you to graph to be able to swoop the ellipse, are my 4 points on my the end of the major and minor axes. So basically our 4 vertices. All right, we have 3 distances that we can define now within this ellipse: A, B, and C. Well, A is the distance from the center of the ellipse horizontally to the edge of the ellipse. More formally, in some other cases, they define it as the length of half of the major axis, this semi-major axis, but we're going to be a little bit more casual in our definition, and we're going to keep A to be strictly horizontal. It helps with some connections to the hyperbola a little bit later in our next video, but we're going to keep A being horizontal. So it's the measurement from the distance from the center to the edge of the ellipse horizontally. And B is the distance from the center vertically to the edge of the ellipse. And then lastly, C is the distance from the center to one of the foci. So I could have labeled A, B, and C a few different ways. A could have gone to the left, B could have gone down, C could have also gone to the right. But I'm just putting these measurements down so we have these 3 defined. So there's a really interesting observation about the sum of these 2 distances, d1 and d2, and the relationship between these measurements. All right. Now, for our purposes right now, A is the distance along our major axis. It's half of our major axis. It's the one through which the foci go through, or it is going through one of our foci. So I want you to notice what happens if I move my point that I'm interested in with this d1 and d2 to the end of this major axis onto the major vertex. So if I set it over there, I can actually measure the length of these things. Notice, I know I can see what these 2 measurements are. I can actually highlight them a little bit right here. So one of our measurements is actually A plus C. So notice if I add C, the orange bit, to the purple bit, the purple length, I get A plus C. So whatever that is always going to be that longer part when I'm over here on the right. And then if I also add on the shorter part, well, the shorter part is C, oh sorry, A minus C. So if I have the length of A and I subtract C, C being from the center to that focus 2, in this case is the one I'm looking at, and I subtract out that bit, I have what I have down here in this red part, this A and C. So notice this length right here, I'm just using it as a measuring stick, but just leaving it down here. So this red distance is right there. If I add those two things together, then I get 2A. All right, so my two distances at this point, if I put xy directly onto that dot, I'm not going to leave it there because then I'll like lose it and can't grab it again. But if I add those two things together, a plus c plus a minus c, the c's cancel to 0, and I'm left with just a plus a, which is 2a. So that means that this distance, the sum of these of d1 and d2, doesn't just equal d, it equals 2a. So this is a pretty big deal. So we can say that whatever my a is, I can just double it and I get the sum of d1 plus d2. Let me move this around a little bit. So if I adjust this focus and move it a little bit, notice here a is 6.06, double it, I get 12.119, which is the same thing as my two d's being added together. So those measurements will always equal each other regardless of where they are. So these blue lines added together is 2a. All right, this time I'm going to move this xy point, instead of being on this major vertex, I'm going to move it up here to where we have this minor vertex. So something important happens right here. Notice if you look at the blue lines and then from one focus to the other focus, what I just created is an isosceles triangle. D1 and D2 are both 5. I'm taking that total distance and I'm cutting it in half. Well, what did we just say? Well, we said that total distance is 2 times A. So that means that one of those distances is just A. So this dotted line that I just created is actually A. I've labeled it A1, but whatever A is, this distance from one focus to the minor vertex is also going to be A. So that means I just created a right triangle. So now I can express via the Pythagorean theorem the relationship between A, B, and C. Do note that the A, B's, and C's here differ a little bit in your probably memory of the Pythagorean theorem, A, B, and C. So be mindful when you're using the Pythagorean theorem that you're referring to legs or the hypotenuse. So if I knew for some reason the A and the C, which could be pretty easy if you knew just the two foci of an ellipse and then a point that is on the ellipse that is on the major axis as well, then that would fully define the ellipse, and then you could find B by using the Pythagorean theorem. So in this case, our B would be 4, and we would get that because that would be the square root of a squared minus c squared. But for our purposes, we're going to be looking at finding C. So I've bolded it for us. So here with this, we have that C is the square root of a squared minus b squared. And so then if I knew the equation, which you'll see in just one sec. Actually, I'm going to go ahead and put it up. The equation for our ellipse, we know our A's and B's immediately because they're going to be in the denominators underneath their x and y counterparts. So then we're going to be able to just pull A's and B's directly from the equation and then find out what our C is. So lastly, I just want to make sure that we're clear about the relationship of this equation. So my numerator, I have x minus h, and the other numerator is y minus k. So that's our h and our k. So remember to sort of kind of flip the signs, just like we did back in college algebra for transformations. So if I move this ellipse, just a sec, let me get rid of that. So if I move this ellipse around, notice that my center is changing along with that, but nothing else is changing. So that's our center. All right, so from this, we can see that A, B, and C are in a right triangle relationship. We know that because the sum of our distances from the focus to the points is 2A. And if we put the point that we're looking at on the minor vertex, then we get this nice right triangle relationship between A, B, and C. So let's go to our notes and take a look at some examples. All right, so here are our notes. Just much of this is just reviewing what we just talked about over in GeoGebra. Do want to point out to remind you that we're defining A as the horizontal distance from the center to the ellipse and B the vertical distance from the center to the ellipse. Some books and websites do that a little bit differently. And in the event when B is greater than A, then we would use this formula that C is the square root of B squared minus A squared, and this just keeps A real. So that's sort of kind of what that means. If you want to take a look at this, you can pause it and look. Here is the derivation of the ellipse, starting with the distance formula, where we go from if the center of the ellipse is at 0, 0 at the origin, and x and y is some point on the ellipse, you can create these two different distance formulas for d1 and d2, add them together, and that equals 2a. And from there we take the two right parts of that top equation and then solve from there and do some manipulations, and then we end up with x squared over a squared plus y squared over b squared is 1. And so that's where we get this general formula, but here we have our h's and k's added in. Just a note, if I was to multiply both sides of our equation, this ellipse equation, this is the standard form of the ellipse as opposed to the general form. The standard form of the ellipse, if I multiply both sides by a squared, notice the a squareds will reduce and left with a b squared on the left part. Here a b squared will reduce to 1 and left with an a squared. And then I could FOIL out these squared binomials, distribute the b squareds and a squareds in, combine like terms, and then we would end up with something in the form of this general term of the ellipse. Now, if I can expand and end up at the general form, that means I can take my general form and complete the square and get to the standard form. One last note before we look at an example. If a and b equal each other, then we're going to get a circle. We saw that with our general form. Specifically, if this a and this c equal each other, then we're going to end up with a circle as we saw in the general form. So in this our equation, if little a and little b equal each other, then let's define those a's and b's to be an r. And so we have this. I can multiply both sides by r squared. And this is the equation of the circle. Oops, I realize I left off my square. Let me fix that. There we go. So this is the equation of a circle, where r is, well, obviously the radius. So when I have a circle, my two foci are actually on top of each other on top of the center. So my two foci on top of each other at the center, and then so a and b then equal each other, and they then just become a radius, and the c would then just be 0. All right, so let's take a look at this equation. So we have 9x squared plus y squared plus 4y minus 32 equals 0. I know that this is an ellipse because we have an x squared and a y squared, as opposed to the parabola when we just had one square term, and then a times c is greater than 0. So that means that they have the same signs, so that way I know that it is not a hyperbola like we'll see in our next video. So step 1, letter A, is I want us to complete the square and then rewrite it in standard form. So to complete the square, my x squared is already in a perfect squared situation. It's not about this 9, it's about this x. All my x's are in a perfect square. So we're good to go there. But this y, I do need to complete the square. So I'm going to add the 32 over to the right-hand side just to get it out of the way. And then I'll set it up and I leave my blanks. And then I half the 4, and then I square it back and get, half the 4 and get a 2. Square it back and get a positive 4. And my coefficient out here is just a 1, so I actually did just add a 4 in on this left-hand side. So I'm going to add a 4 onto the right-hand side. With the parabola last time, I kept the constant on the same side, I believe. So in that case, I would need to then have to subtract a 4. But here, because I'm adding my constants to the right-hand side, it's going to be more efficient that way. I went ahead and moved it over with that positive 4. All right, so then I add my terms together and I get 36. And then I can divide everything by 36. So when I divide everything by 36, The 9 and the 36 reduce to a 4 in the denominator. Nothing reduces, and we just have a 36 here. And 36 over 36 reduces to 1. So now we have our standard form of the ellipse. So a few things that are happening here. So first up, our h is 0. There's inside of this x and x minus 0 squared, if you want to think of it that way. So that's how I know that my h is 0. My k is a negative 2 because there is an already understood subtraction here, or just swap the signs. So that tells me right off the bat that my center is at 0, negative 2. All right, now what about my a's and b's? Well, one thing before I even worry about that, I should notice that since the b is bigger than the a, my b squared is bigger than my a, it's going to be a vertical ellipse. It's going to be taller than it is wide. And that's just because, remember, we're keeping the b's with the y's. So if my a squared is 4, I square root it to get 2. My b squared is 36, square root it to get 6. So just as a quick sketch of it, so I have these points where I know I'm going to go over to 2 and up to 6 here, and then we just smoothly connect all the way up there and then wrapped all the way around. So this is how I know that it's that vertical ellipse. Because it's a vertical ellipse, I'm going to then have my major axis be vertical. It's the longer of the two axes, and it's vertical, and it's passing through my center. So since it's a vertical line, if it's a vertical line, then it's going to be an x equals value. So that's x equals 0. It's going through the center, so just take the x value from that center. All right, so now what about our major vertices? How do we find that? All right, so remember how I said over here, I have my center, and I'm going to go left and right 2, and then up and down 6. Well, let's just do that, but let's just stick some numbers on it. So if I know that I have here at 0, negative 2, and if you were to go right 2 units, if you were to go back and ask your 5th grade self, hey, 5th grade self, here's, if you're standing at the point 0, negative 2, and you go right 2 on the coordinate grid, where are you going to be now? You don't need formulas to be able to do this. Just add 2 to your x's because you're going right 2. So now we're at 2, negative 2. Go left 2, and now you're at negative 2, negative 2. If I take my center and I go up 6, now I'm just going to add 6 to my y value, and I'm at 0, 4. If I go down 6, I'm going to subtract 6 from my y value, and I'm at 0, negative 8. So those are my vertices, my major vertices, negative 2, and 2, negative 2. My minor vertices, 0, negative 8, and 0, 4. All right, next I need to find what's called the focal length, distance from the center to one of the foci. So because the b is bigger, we're going to put the biggest one first, or just think about it, it just needs to be real. So if you're subtracting and you end up with the negative, just swap them and use that version of the formula. So square root of 36 minus 4, that's square root of 32, which simplifies to be 4 square root of 2. 4 square root of 2, just FYI, is about 5.6. So then where will my foci lie? Well, again, because this is vertical, my foci are going to be above and below the center. So take my center and go up 4 square root of 2 and go down 4 square root of 2. So take this negative 2 and add 4 square root of 2, and then take the negative 2 and subtract 4 square root of 2. And that's where my foci are going to be. All right, now let's graph it. So when it comes to graphing, I like to graph just my center first, and then I graph my vertices. And when I do that, that just helps make sense to make sure that I am graphing those correctly. This is a distance of 2. This is a distance of 6. So we're kind of self-checking that way. And then my foci need to be inside the ellipse, and the skinnier that it is, the further away and the foci will feel from the center, and the closer these are going to be, the skinnier that it is. So then plot those and label all of your points. And then one last little thing is for us to find our x and y intercepts. Well, good news about our y-intercepts is that they are our major vertices, so that's good. But then to find our x-intercepts, we need to let y equal 0, plug in a 0, and so we just have 2 squared, which is 4. Then rewrite this so we have it equal to 32. Square root, divide by 9, square root both sides. Don't forget the plus or minus. And when I square root that 32 ninths, remember we then square root the 32, and that ends up with that 4 square root of 2. Square root of the 9 is 3. So this is about 1.87. But if you drew your ellipse correctly, your x and y intercepts should already be pretty well labeled and in the correct location, so that I'm just labeling it. So this is x2 and x1. One little labeling trick is if somewhere near your graph, if you have a point and you label it as such, so x1, x2, like that. Actually realized I have my 1s and 2s switched. There we go, that's better. So if I have this point labeled as x1, so then I can just label that's x1. This point's labeled x2, so I can have that point labeled as x2. So there we have it. We graphed our first ellipse. We graph our center. Remember, this distance is the A. This distance is the B. The distance from the center just to that focus is the C. And we were able to get that because we know that that's a right triangle. From here to there is our A. Rather, actually B in this case, but that would be a B. That's our A there. And then here we can then get our C from this right triangle. All right, let's take a look at our last example. All right, so we have 16x squared plus 25y squared minus 96x plus 100y minus 156, and we're going to do the same set of things. All right, so we need to complete the square, not once, but twice. So let's add the 156 over to the right-hand side. And then remember, the leading coefficients always need to be 1 before you complete the square. So I'm going to factor a 16 out of my x's. Oh, and I rearranged my x and y terms, the x and y linear terms, so that way they are with their friends. All right, so then I factored 16 out of the x's, factored a 25 out of the y's, and then we can do our completing the square. So -6 halved is -3, squared is 9. Now I'm adding 9 into here, but on this left-hand side, I'm actually adding a 9 times 16, which is 144. So I add a 144 to the other side. For my y's, I halve the 4 and I get a 2. Square it back and I get a 4. Now I added a 4 inside the parentheses, but on this left-hand side, I added a 25 times 4, which is 100. All right, so then I add these things together and I end up with 400. And then divide both sides by 400, and we end up with 25 and 16. Most likely, you'll get decently, probably squared numbers or numbers that are friendly enough. So you should usually have things reduce out. Everything at least should reduce out, so that way we don't have a 1 in the numerator. If not, then you'll need to adjust and kind of force it. All right, so our h and our k is 3 and -2. Basically flip those signs. So our center is at 3, -2. We're going to go right 3, down 2. Then our a squared is 25, so that means our a is 5. Our b squared is 16, so that means our b is 4. So I can use that information to make our ellipse. So I have my center at 3, -2. For my major axis, then I'm going to go right and left 5. And so I get 8, -2, and -2, -2. For my minor axis, I'm going to go up and down 4. So up 4, add 4 to the y, and we get 3, -2. Subtract 4 from the y, and now we get 3, -6. So there I have my 4 vertices. All this work over here to the side is just sort of kind of scratch work to myself, just so I can put my thinking down on paper to be able to visualize this a little bit. So that's where I get my 4 vertices. Then for my C, because this is a horizontal ellipse, I know that it is a, I forgot my major axis. My major axis is this dotted line. It is horizontal because it's a horizontal ellipse, because the a squared is bigger. Since it's horizontal lines are y equals. So we have y equals -2, and it's going to be the y value of the center. So like I said, because it's horizontal, I then have my a squared minus b squared. That will give me a positive number. 25 minus 16 is 9. Square root of 9 is 3. So we have a nice, easy 3 for the distance of the focal length. Generally speaking, when we set up our equations, we're probably going we're going to err on the side of giving you nicer A's and B's, and probably usually uglier or more square roots, not perfect integers for the C. So don't freak out if you get square roots on the C like we did last time. So I take my center and I'm going to go left and right 3. Going left and right because it's a horizontal, it is wider than it is tall. So add 3 to the x and subtract 3 to the x, and that's how we get our two locations of our foci, the coordinates of the foci. All right, so now for my to graph my ellipse, I put my center at 3, -2. I go right 5, left 5, put my vertices. Then I go up 4, down 4, and put those minor vertices. And then right 3, left 3 for the focus. If you somehow were tempted to go up 3 and down 3 for these foci, when you get to graphing, you should realize that that's not right. Kind of, I don't know, think again how everything wants to feel nice and balanced, or in terms of science, like if these are like during the process of cell splitting, these are like the two nuclei and they're like moving apart from each other. If I was to be moving the two nuclei apart from each other and I move it vertically, it's not going to get a the oval, this ellipse is not going to be wider than it is tall. All right, does that make sense? So the picture should be sort of kind of self-correcting if you were moving the foci in the wrong direction. All right, so once you get these 4 points, your 4 vertices, then you can easily swoop your ellipse with our foci labeled for clarity. And then let's just, for good math habits, let's find our x and y intercepts. Remember, we can have more than one y-intercepts because this is not a function. So to go through this math, again, I'm starting with this equation, but I'm multiplying everything times 25 times 16, so that way I can just get rid of fractions. So I'm multiplying everything times 400, and then here I go from here. I plug in 0 for my y, which leaves me with just 2 squared, which is 4, combined like terms, and I can divide out this GCF of 4 to make my life easier, and I end up with this. You can try factoring it, it's not going to work, can't factor, so we use the quadratic formula, and with our quadratic formula, our discriminant ends up being, after you take the square root of the discriminant, 20 square root of 3, and then we can reduce, and we get 3 plus or minus 5 halves square root of 3. That's my x-intercepts, and that ends up putting them here. And notice this 3 right here, that is this 3, which is the location of the x value of the center, or that minor axis. So it's that 3 plus or minus that same distance. And then my y-intercept, we do the same thing, but this time we're letting x be 0. So it's going to feel very familiar. But we get to this quadratic, this one, and we try GCF. There's not a GCF in common. So then we do this big AC, and we get AC is negative 3,900, and we end up with actually 30 and 130 are factors of 3,900, and if I use a negative 30 and a positive 130, they add up to be 100y. So then I factor, and I end up with 5y minus 6 and 5y plus 26, and we end up with my y-intercepts being 6/5 and negative 26/5. And so then again, if you're at, it's basically -2 plus or minus that same amount of a fraction, which is 1, 2, 3, and a sixth, or 1, 2, 3, and a sixth. All right, so there we have it. There's our there's how we graph our ellipses. We start with our an ellipse in the general form. We complete the square to put it into the standard form, and then from there we can then graph it using our vertices, and we find our foci, and then just for good mathmanship, we then find our x and y intercepts. I hope this helps you be successful in your homework, and we'll see you in the next video.